Okay, everybody, welcome back to another video from Mrs. Semino. Today we're going to be talking about Chapter 9 and Stoichiometry. As always, I would suggest reading the chapter to better help you understand the concepts that we're going to be talking about. So there's the pages. So on this first slide here, we're going to go ahead and define what stoichiometry means. And I know this word looks a little weird. This Y should be up here for stoichiometry. And so the definition you'll want to know for your test is the study of the quantitative or measurable relationships that exist in chemical formulas and chemical reactions. So for me, what this really means is last chapter, we really talked about how to write chemical formulas. Now we're going to be able to use those chemical formulas to figure out how many reactants we're going to need and figure out how many products will be produced with a given number of reactants. So you're going to be using the skills that we've learned from the last two chapters here in this chapter to be able to write those formulas. Remember that the coefficients represent moles. So before we can get into the exciting world of stoichiometry, we need to remember, and I know we talked about this a little last chapter, how to read a chemical formula. So if I was to look at this one that we have here, and remember you guys, sorry, it always looks fine on the PowerPoint, but when I convert it over to the video software program, like this 2 should be a smaller subscript, this box should be this arrow here, smaller subscript. So I hope that you guys are getting that. So the idea here is there's a couple of different ways we can talk about this. So if I could say that I have 2 molecules of hydrogen reacting with 1 molecule of oxygen produces 2 molecules of water. So we can use a thing called molecules, and so we're talking like on a really microscopic scale, you can't see them. But I hope you remember the other way that we can use these coefficients out front is to discuss moles. So the other way that I can read this formula is 2 moles of hydrogen gas react with 1 mole of oxygen gas, yield or produces 2 moles. And so I'm hoping that you remember that a mole is 6.02 times 10 to the 23rd, and in this case we're talking about molecules. So that's a lot of molecules. So initially when I read this we were only talking about 2 molecules. Now we're talking about 12 times 10 to the 23rd molecules of hydrogen gas in this equation. So one of the very first things that we're going to need to learn in this chapter is how to do a mole ratio. So this is going to be like one of the key things that you learn, and that's going to help you solve these crazy stoichiometry problems that we're going to see in a little bit. So here we go, mole ratio. And it is indicated by the coefficients in a balanced equation. So again, here's our balanced equation. And again, this box here should be the arrow. We should have these subscripts here. Sorry about that. So if I was to ask you what is the mole ratio of hydrogen to water, you would say it's a 2-to-2 ratio. And the reason that you would say it's a 2-to-2 ratio is I have a coefficient of 2 out front here and 2 here. So for every 2 moles of hydrogen gas that's going to be reacted, we're going to produce 2 moles of water there. So that's why our ratio here is going to be 2-to-2. Now, if we were to look for the mole ratio of oxygen to water, well, even though it's not written here, remember there's like an imaginary 1 here. So our ratio of oxygen to water is going to be 1-to-2, and that's because I have the 1 here and the 2 here in front of the water. So the mole ratio of oxygen to water is 1-to-2. So here we're just kind of reviewing some of the terminology. Again, this should be the arrow here. In that, if we say that we have 2 moles of hydrogen react with 1 mole of oxygen, again, remember that imaginary 1 is there, to produce, or we might say yield, 2 moles of water. Again, we've got this coefficient 2 moles of water. So another way that we can look at an equation is in terms of mass. So we can say that we have 4 grams of mass, 4 grams of hydrogen, 32 grams of oxygen, and 36 grams of water. And so you're like, well, where did you get these values for? You're going to go ahead and see them at the bottom of the next slide. So the way the calculations work to show that there's 4 grams of hydrogen is that we have 2 moles of H2. And so notice we take the 2 moles, we just do a little multiplication and division. We put the 2 grams over the 1 mole. And this is that conversion where we take 1 mole equals the molar mass. And the molar mass of hydrogen, H2 is 2 grams, right? Hydrogen is 1, and there's 2 of them, so that's why it's 2 grams. We can also say that we have 32 grams of oxygen, because if we look up here, there's the imaginary 1. 1 mole times 32 grams divided by 1 mole is 32 grams. Again, this is the molar mass of O2 over 1 mole. And then we can say that we had the 36 grams of water because we have this coefficient of 2 here, so 2 moles. Molar mass of water is 18 divided by 1 mole. And then so this stuff that you can see here in the red, it just says that the law of conservation of matter and mass is verified via our 4 grams plus 32 grams equals 36 grams. So basically we're not creating or destroying any mass in a chemical reaction, and that's really important for you to recognize. Another way that we can look at an equation is in terms of molecules. So in this case I can say that I have 2 molecules of hydrogen gas and 1 molecule, remember we've got that imaginary 1 out front here, of oxygen gas yields, again this little yield sign should be here, 2 molecules of water. And so you can see this equation, or this sentence here, 2 hydrogen molecules react with 1 oxygen molecule to produce 2 water molecules. So notice that the number of molecules is not the same on each side. And we talked about this, about how it doesn't have to be equal on both sides. Another way to talk about this is in terms of atoms. So we might read this equation. 4 atoms of hydrogen react with 2 atoms of oxygen to produce 2 water molecules, which are 4 atoms of hydrogen and 2 atoms of oxygen. And another way that it seems a little unusual that we can talk about it, but we're definitely going to use this in stoichiometry, is talking about this in terms of volumes. And so the volume that we're going to be using is liters. So what we can say is we have 44.8 liters of hydrogen gas reacts with 22.4 liters of oxygen gas to produce 44.8 liters of water. And so you might be like, well, where did you get this 48 and this 22? Well, I'm hoping you remember this equation we said that 1 mole is equal to 22.4 liters. This is one of those conversion factors that we had written down in our notes a while ago. So the reason that we can say that we have 44.8 liters is because there's 2 moles of it. So we're going to take 22.4 and multiply it by 2 to get the 48.8. So it does say down here, notice that the number of liters of gas is not the same on each side of the arrow. So remember that when we talk about molecules, we talk about atoms, we talk about liters, they're not going to be the same, but the number of atoms does need to be the same on both sides of the equation. So let's go ahead and look at a practice problem, and it reads that lead will react with hydrochloric acid to produce lead 2 chloride and hydrogen. And the question is, how many moles of hydrochloric acid are needed to completely react with 3.6 moles of lead? And so right now you're like, oh my goodness, where do I start? So let's go ahead and take a look. So the first thing that you need to do is to write that equation and make sure that you're balancing it. So lead will react with hydrochloric acid to produce lead chloride and hydrogen. So here's our lead, here's our hydrochloric acid, here is our lead 2 chloride, and so you have to remember that how to write that formula. And then hydrogen, this is our diatomic molecule, so it's going to be H2. Now we need to balance it. I notice that there is 1 lead on both sides, so that's lovely. But initially, we only have 1 chlorine and 2 chlorines, so we need to add this coefficient out front here. Then that also gives me 2 hydrogens. I have 2 hydrogens on the product side, so everything is balanced. The next step to do is to determine the mole ratio. And so hopefully you're going to do this tomorrow or you've already done it, the mole ratio packet, so you should be well familiar with mole ratios by the time you start making these calculations. So the second part of that question was asking how many moles of hydrochloric acid are needed to completely react with 0.36 moles of lead. And so what we need to do is we need to find lead. We need to find hydrochloric acid and look at these coefficients. Lead has that coefficient of 1, and hydrochloric acid has a coefficient of 2. So we need to kind of set this up between the wanted and the given. And so the way that this is going to look is we're going to take what's given, which is the 0.36 moles of lead, and we're going to multiply it by the mole ratio of hydrochloric acid to lead. And notice that these two are going to end up canceling, and it's going to leave us in our wanted value of moles of hydrochloric acid. So I got this 2 because there's a 2 coefficient out in front of this HCl. I got this 1 because there's a 1, an imaginary 1, I know, but it's still just a 1 there. And so we just go ahead and do the math. So we're going to take 0.36 moles of lead, multiply it by 2, divide it by 1, and again these cancel. And so our final answer is 0.76 moles of hydrochloric acid is what is going to need to completely react with 0.36 moles of lead. Make sure you guys write this example down so when you do your problems on Friday, you'll know exactly how to do them. So here's just another cute little baby picture. It would require 0.72 moles of hydrochloric acid, is that right? And yes, it is correct. Don't you wish you were this small and could understand stoichiometric problems? So this was just a funny PowerPoint. It's got this lady from Harry Potter. Hopefully you guys remember her. So you guys actually do have more than 9 problems to still practice. And in fact, I'm going to go ahead and on the next slide show you how to do a few other examples that you're going to need. Okay, so on that last example problem, we basically were going from moles of one substance to moles of another substance. And the thing that you're going to use to help you get there is you're going to use that thing called the mole ratio. Okay, so that's where we look at the coefficients in our chemical equation, and you just set them up how you needed to get your needed item. Now, one of the other things though that we're going to be doing in our practice problems is we're going to be going from liters, and remember that's a unit for volume, to moles. So I would say liters of A, then over to moles of B. So kind of like as we do this flow chart, like check this out. So if I'm given liters of A, I can get into moles of B by following this chart. And so what you want to do here is to get from liters to moles is you would multiply whatever your liter value is by 1 mole of the substance divided by 22.4 liters. Okay, so let's just say it was 2 liters. Notice that our liters then would cancel top and bottom and you're left in moles. So like I was saying, if they give you liters of A and ask you for moles of B, it's pretty simple. You do have to have a couple of conversion factors, and that's going to be this first conversion factor, and then you're going to use the mole ratio to determine the moles of B. Another thing they might ask you to do is to go from grams of A to moles of B. Okay, so starting off with grams, or this might be our mass, and we're going to get to moles of B. But before we can't just straight go from grams of A to moles of B. We have to take a stop at moles of A. So what you would do then is you would just multiply by the 1 mole over whatever the molar mass is, then you have the moles of A, then you use the mole ratio to get the moles of B. Likewise, you can also be asked to go even further in your problems by asking to get to, for example, liters of B. So the way that you would do this, if you were given liters of A, then ask for liters of B, you can't just notice there's no arrow that's getting you straight from here to here. You have to take this route of going from liters of A to moles of A, using the mole ratio to get to moles of B, and then convert it into liters of B. And the way that you would do that then is to multiply it by 22.4 liters divided by 1 mole. Okay, and then finally the last one that it might ask you to do is to get it into grams of B. And so whatever your route is, let's say that you are sort of giving grams of A and ask for grams of B, the route that you would have to follow is you would have to go from grams of A, convert it into moles of A, use that mole ratio, get into moles of B, and then get into grams of B. And you would do that by just using a little bit of math and taking the molar mass divided by 1 mole, okay, to get your grams of B. And you can do this a couple of other ways too. You might see in some problems they give you liters of A and ask for grams of substance B. And so in that case you would just simply convert from liters to moles of A, use the mole ratio, get into moles of B, and then convert into grams of B. So I hope this flow chart's kind of making sense. Please ask your neighbors, somebody else in class if this isn't making sense.